Welcome to the lecture number 4. So today we will study the separation axioms. So in this chapter there are mainly 4 types of topological spaces. So first of all we have Tikhonov topological space. First of all we have Tikhonov. So Tikhonov topological space. So what is Tikhonov topological space? So a topological space x tau is called Tikhonov if any two disjoint points in X are separated. That is, for any 2 points, say x and y, for any 2 arbitrary points, there exists an open set containing x, say that open set is U, open set U containing x such that y does not belong to U. Okay, and this topological space is also called the T1 space. So this topological space is also called T1 space. Okay. Now, can you give one example what is a Tikhonov space? So in general, which topological space we know, most of them are Tikhonov space. So we can give one example which is not a Tikhonov space. So first of all, so if we take x equal to just 2 point a comma b and take the indiscrete topology, that is tau equal at empty set singleton A, sorry, not singleton A, we will take empty set and this AB. We take that indiscrete topology. Now you can see that if we choose the points A comma B belongs to X, then there is no Y, no open set, containing A which do not contain B, right? Because the only open set containing A is that AB, that is the whole set, right? And it will also contain B. That's mean this space is not T1. that imply that topological space x tau is not a T1 space. So what is the example of T1 space? So can you give one example which is a T1 space? So almost all topological space other than this one is a T1 space. For an example, if you take discrete topology, this is T1 space. If you take any matrixable topological space or matrix space, that is also T1. So anyway, so we will see these examples later. Now this is the example of that T1 space. Now we move to the next topological space, that is T2. That's when it is called Hausdorff. Hausdorff topological space. So you already know the definition of this, right? So let X be a topological space so anyway, so topological space means X comma tau, right, with a topology. So here I am just exclude that term, the tau. Okay, so let X be a topological space, then X is called Hausdorff if for any 2 points are separated by open neighborhood. That is, for any 2 points, say x comma y belongs to X, there exist open sets or open neighborhoods ux and say uy such that X belongs to ux, y belongs to uy, and ux intersection uy equal to empty. Now it is easy to see that if a topological space is Hausdorff, then it is T1 as well, right? Now the Hausdorff topological space is also called T2 space. Now it is clear that it is easy to see that it is by the definition T2 imply T1, right? Now what about the converse? But the converse is not true, but T1 does not imply T2. Now can you give one example which is T1 but not T2? Okay, now the example is, that is one of the example is, that is line with two origin. So line with two origins is T1 but not T2. So what is the line with two origins? So we have seen that, right? So the topological space, first of all, let X equal to R cross 0 union with R cross 1. Okay. Now take the identification, that is X cross 0 will be identified with X cross 1 if and only if X not equal to 0. Then the topological space X quotient with this will be this. That is, this is my one line, this is my 0, right? And this is another point, this, right? Because all of the other point of this line, if we take the other point of this line, right? So this point is identified with this point is identified with this point, right? But this point and this point are not identified, right? So they are not identified. But these are identified. Now by the construction, it is easy to see that this topological space is T1. Why? Because if we choose any 2 points in this line, right, then you can actually separate them by open neighborhoods. So obviously they are separated. If we choose one point here and one of this point, say this one, this and this, then also we can get two disjoint open sets which contains them, right? This is also done. That's mean this topological space is T1. And even if we choose this point, that is this point, now if we choose this point at this point, then also we can get a open neighborhood containing this, say this one, which will not cover this point, right? That's mean they are separated. But we have seen that this topological space is not Hausdorff. Why? Because of these 2 points, right? Now if we choose any open set containing this point, then it will be this kind of open set, right? Open neighborhood. Again, if we choose this point, and its neighborhood will be again this open neighborhood, that is this u minus, suppose this is my x, this is my y, minus x union y, right? That's mean this point x and y are not separated by open neighborhood. That's mean this is not a Hausdorff topological space. So now we move to the next topological space, which is called regular. That is regular topological space. So let X be a topological space such that one point sets are closed in X. Then X is called regular if for any pair X, B that is x belongs to x and B is a closed set in X. So for any such pair, there exist open sets Ux and Ub such that X belongs to Ux and B subset of UB and UX intersection UB, their intersection is empty. That's mean if we choose any two pair of a point and a closed set, then they are always separated by open sets. Now, if a topological space satisfies this property, then we will say that the topological space is regular. And this space, so the regular topological space is also called T3 space. Now note that why do we need these conditions, that is that one point sets are closed in X. Why do we need to include this property? Because of this property we can say that T3 imply T2. So if we exclude this property, then we cannot say that T3 imply T2. Why? Because since the one point sets are closed in X, that's mean if we choose any two points X and Y, right? Then that point Y, you can treat that point Y as a singleton set Y. And since the one point sets are closed, so singleton Y is closed. So we can call it B, right? Then we can get two disjoint open sets containing X, containing the point X, and containing the set singleton Y, right? That's mean this is Hausdorff as well. That's mean we get two disjoint open sets U and say B, or Ux or Uy, so that Ux containing X, Uy containing Y, and Ux intersection Uy, their intersection is empty, right? That's mean T3 implies T2. So we can write that one. Since one point sets are closed in X, so T3 implies T2. Now the question is, if we remove these conditions from the definition of the regular topological space, then can we say that T3 implies T2? The answer is no. If we remove this condition, then we cannot say this. Why? Because you can choose the topological space X equal to only 2 point set A, B, and you can choose tau equal to the indiscrete topology, that is empty set and AB, right? Now suppose your X, that X is just a point A, then what will be your B? So B is a closed set disjoint from A. Now what are the closed sets in tau? The only open as well as closed sets in tau is only empty set and AB. Therefore, if this is my X, then my B will be this empty set, right? Now this is the only possibility, right? Now one can choose the open set containing A, that is you can choose my ux equal to AB, and you can choose that empty equal to my set UB. Then ux intersection UB equal to empty, right? Now this is true for any pair of points and closed sets, right? Therefore, this topological space is regular, right? So therefore, this topological space is regular. But we know that this topological space is not Hausdorff, right? But this is not Hausdorff. Because if we choose any 2 points, say A and B, then we cannot separate them by the disjoint open sets, right? So this is an example of regular topological space which is not Hausdorff if we remove these conditions. Therefore, this condition, that is 1 point sets are closed in X, is very necessary. Anyway, now we see that the converse is not true. That is, but T2 does not imply T3. That's mean if we have a Hausdorff topological space, that does not imply it is regular. For an example, RK is Hausdorff but not regular. So we shall see this one, that is these examples later, but now I shall define the next topological space, that is the normal topological space. Normal topological space. So again, so let X be a topological space such that 1 point sets are closed in X. Then X is said to be normal if any pair of closed sets are separated by open neighborhoods. That is, for any two closed set, say A and B, so there exist open sets or say open neighborhood UA and UB such that A subset of UA, B subset of UB and UA intersection UB is empty. Now, from this definition, it is clear that normal imply regular. Why? Because of this one point sets are closed in X. So therefore, if a topological space is normal, then we can take one of this a singleton X, right? Now since the singleton sets are closed and any two closed sets are separated, therefore if we choose any point and a closed sets, then they are also separated by the open neighborhoods. Therefore normal topological space will also imply the regular topological space. Now, so the normal topological space is also called T4 space. Okay. Now since one point sets are closed in X, therefore T4 will imply T3. That is normal imply regular, but the converse is not true. But the converse is not true. That is T3 does not imply T4. That's mean the example is RL cross RL. Now this is regular but not normal. So therefore we get the Tikhonov topological space T1, right? We get the Hausdorff topological space T2, we get the regular topological space T3, and we get the normal topological space T4. So this is Tikhonov. This is Hausdorff. This is regular. And this is normal. And we know that T4 imply T3, this is T3 imply T2 and T2 imply T1. But the converse is not true. That is, this is not true. Here we get the example RL cross RL, that is which is regular but not normal. Here we get RK, right, which is regular, Hausdorff but not regular, and here we get line with two origin. Two origins, which is T1 but not T2. Now we prove that the topological space RK is Hausdorff but not regular. So example, the topological space RK is Hausdorff but not regular. So first recall what is the topological space RK. Now recall that the basis for RK is the open interval of the form that open interval AB and as well as AB minus K, where K equal to the set 1, 1 by 2, 1 by 3, this. Okay, and AB belongs to R. Right? Now it is easy to see that it is Hausdorff, because for any two points x less than y in R, we can choose u equal to x minus 1 comma x plus y by 2 and v equal to that x plus y by 2 comma y plus 1. So choose this, then x belongs to u, y belongs to v, and u intersection v equal to empty, right? So RK is Hausdorff. Now we claim that RK is not regular. Now to prove that it is not regular, we need to find one point and one closed set such that they are not separated by open neighborhoods, right? Now first of all, we claim that K is closed. So it is actually clear that the set K is closed in RK. So if you cannot see this one, why K is closed, I can prove this one. That proof is very simple actually. So we know that minus n comma n minus K is open in RK, right? Therefore union over this, sorry, we can take just n, natural number minus n comma n minus K, this collection is just R minus K is open, right? That implies since K complement is open, so K is closed in RK. Now choose the point 0 belongs to R. Now we claim that 0 and the closed set K are not separated by the open neighborhoods. Actually it is very easy to see that, but little difficult to prove. Okay, now claim the point 0 and the closed set K are not separated by open neighborhood. Why? So if possible, there exist open sets U and V such that 0 belongs to U and K subset of V and U intersection V equal to empty. So if possible, there is such disjoint open set, one contains 0 and another consists the subset K. Now we get a contradiction. Okay, so what kind of contradiction we get? First of all, we have 0 belongs to U. So choose a basis element B such that 0 belongs to B subset of U. Now we have all the basis element is of the form either open interval AB or open interval AB minus K. Now what kind of open interval this be? Now it is easy to see that since U intersection V is not empty, now since U intersection V is empty, that imply B intersection K, right, is empty, is also empty. That imply B is of the form that A B minus K, right? Because if B is of the form only closed in open interval AB, then it must contain some elements of K, right? It is easy to see that. Therefore, B is of the form this. Now, we know that imply 0 belongs to that open interval AB. Now since and there exists a large N such that 1 by N belongs to AB, right? This is true. This is true by the Archimedean property, right? We have a large N such that 1 by N belongs to AB. Now that will imply 1 by N plus 1, 1 by N, this set, open set, subset of AB, right? This is also clear. Fine. Now we know that since that 1 by N belongs to K, which is subset of V, right? So let a basis element, say B dash, such that 1 by N belongs to B dash subset of B. Now what kind of B dash will be here? Now obviously we know any basis element is of the form either open interval AB or open interval AB minus K. Now since this basis element contains one element of K, so it cannot be open interval AB minus K, right? Now that imply, or we can write that since B dash intersection K is non-empty, so B dash is of the form only C D, for some CD belongs to R, right? So that implies 1 by n belongs to C comma D subset of V. Okay. Now let or consider the open set C comma 1 by n. And we can say that this is subset of V, right? Now we get this is subset of AB, subset of U, and this is subset of V. Again, let W equal to that 1 by n plus 1 comma 1 by n intersection C comma 1 by n. Now obviously W is non-empty because it is intersection of two open sets with one in point, right? And because W is just, because why it is non-empty, it is clear, right? Because W is just of the form, say, E comma 1 by n, where that E equal to maximum over 1 by n plus 1 comma C, right? That's when W is non-empty. Now this imply W subset of 1 by n plus 1 comma 1 by n, and we have seen that that is subset of U here, right? So this is subset of U, and W subset of C comma 1 by n, which is subset of V, subset of V. That will imply W subset of U intersection V, and this is a contradiction. Therefore, RK is not regular, right? So we got a topological space X, that is the RL, which is Hausdorff but not regular. Oh, this is RK, right? RK is not regular. Now we claim that RL cross RL is regular but not normal. But for this we need some basic theorems because it is a little bit difficult to prove these statements, right? So before going to this example, I shall prove some theorems, and then maybe in the next lecture I shall prove this result. Now today in this lecture we shall see some basic theorems. Now before going to the proof of the theorems, I want to state two basic results in the set theory, that is two elementary results. So I know all of you know all of these basic results, but still I want to state that one because so that no confusion arises. So first of all, for any two subsets A comma B subset of X, A intersection B is empty. This is imply both sides, this is equivalent to A subset of X minus B or B subset of X minus A. Now this is clear, right? Why? First of all, assume this, right? Now we claim this. Now assume this one. Now we want to prove this one. Now choose a point X belongs to A. Now since X belongs to A, so and X and A intersection B is empty, so X cannot be in B, right? Therefore X, so we can write now since A intersection B is empty, that implies X cannot be in B, that implies X belongs to X minus B. Therefore A subset of X minus B. And similarly we can prove that B subset of X minus A. And this is true conversely as well. Why this converse is also true? Now let X belongs to A. Now that will imply X belongs to X minus B, right? Now that implies X is not in B. Therefore if something in X, then that should not be in B. Therefore A intersection B should be empty. Now this is one observation. Now another observation is for any two open sets say U V subset of X. Now U intersection V is empty will imply U closure intersection V is also empty, or you can say U intersection V closure is also empty. The proof is also simple. Why? Since U intersection V is empty, okay, now that will imply U subset of X minus V, right? Now what is V? V is an open set. Therefore this is an closed set. Closed set. Now U subset of a closed set. Now what is U closure? U closure is the smallest closed set containing U, right? That will imply U closure subset of X minus V, and again that will imply U closure intersection of V is empty, right? So these are the two basic results in the set theory which we will use in our next theorem. So what is the theorem? So let's go to the statements of this theorem. So let X be a topological space such that one point sets are closed in X. Then the theorem says X is regular if and only if given a point X in X and a neighborhood U u of x, there exists another neighborhood v of x such that v closure subset of u. That is in other words, so if x belongs to u for some points x in x and open set u in x, then there exists another open set v such that x belongs to v and v closure subset of u. Okay, now we will prove this theorem. First of all, assume that x is regular. X is regular. So assume that x is regular and we will prove the given condition. That's mean choose an arbitrary point x in x and open set u containing x. Now we will prove the existence of such v. Now it is given that x belongs to u and u is open, right? Now that implies x minus u is a closed set disjoint from a. Disjoint from the point x, right? Now since x, given that x is regular, since x is regular, so there exist open sets v and w such that x belongs to v, that x minus u, the closed set this subset of w, and v intersection w is empty, right? Now given that v and w, or not given, so here these are open, right? Now by the set property, that imply v closure intersection w is empty, right? Now since x minus u subset of w, that imply v closure intersection x minus u, that is also empty. Now that imply v closure subset of u. So we got that required v, that imply x belongs to v and v closure subset of u. So we get the required condition. So this is the required conditions, right? Now we prove the converse of this. converse. Now assume that for any given point x of x and a neighborhood u of x, there exists open neighborhood V such that x belongs to V and V closure subset of U. Suppose this is true for any pair of U and X, right? Now claim X is regular. So we prove that for any pair of one point and a closed set, they are separated by the open neighborhoods. Okay, so let x belongs to x and C be a closed set in X. Okay, now let U equal to the complement of C, right? Now that implies X belongs to U and U is open. Now by the given condition, there exists V such that X belongs to V and V closure subset of U. So now what is my C? So it is given that U equal to X minus C, that is U equal to C complement. So that implies C equal to U complement, right? So therefore C equal to X minus U and this is subset of X minus V closure. Also V closure is closed, so X minus V closure is open. So call it W. So let W equal to X minus V closure. Now then it is also easy to see that V intersection W is empty. V intersection W is empty. Why this is empty? As V subset of V closure, that imply V intersection X minus V closure is empty, right? Okay, so therefore we had two arbitrary pair, that is one is point X, another is the closed set C. Therefore for arbitrary X and closed set C in X, we have open sets V and W such that X belongs to V, C subset of W and V intersection W equal to empty. Now this implies X is regular. Therefore the given condition is equivalent to the x is regular. So this is one of the main theorem. We will use this theorem again and again to prove some results. So this is for today only. So in the next lecture, I shall continue with this. So we stop here.